So my name is Lucie PERAT. I'm a PhD student working at the LBE, the Environmental Biotechnology Laboratory in France, Narbonne. Today, I'm going to talk about the impact of the composition of organic waste on biohydrogen production by dark fermentation. But first, let me introduce quite quickly dark fermentation, as it was already presented before. So dark fermentation is a part of an anaerobic digestion process. We are going to suppress the last step, methanogenesis, to prevent the consumption of hydrogen by methanogen archaea. This way, we will be able to accumulate hydrogen, CO2, and VFA, mostly acetate and butyrate, in the media. Hydrogen can be produced either by following the acetate pathway, the butyrate pathway, or a combination of both in mixed culture. One of the major problematics of dark fermentation is homoacetogenesis, which corresponds to the consumption of hydrogen and CO2 by homoacetogen bacteria to produce acetate. It remains a problem for dark fermentation because we are not fully able to completely eliminate the homoacetogen activity during dark fermentation and during dark fermentation conditions. We can calculate the HPE, hydrogen production efficiency ratio, to estimate if acetate production was related to hydrogen production or homoacetogenesis. When the ratio is equal to 1, we consider there is no homoacetogenesis. On the contrary, when this ratio is below 1, we can suppose that there is some homoacetogenesis activity and therefore hydrogen consumption. It is well known that the substrate nature has an influence on hydrogen yield during dark fermentation. In particular, as it was presented before, it's mostly carbohydrate-rich substrates that are the most appropriate substrate to produce hydrogen. But sometimes when we are mixing substrate of different composition with different contents on carbohydrates, proteins, or lipids, we can observe interactions. These interactions were identified in the literature by comparing the theoretical and experimental hydrogen yield. The theoretical yield corresponds to the sum of the individual yield of each component of the mixture. In the literature, we observed sometimes no interaction, therefore the theoretical and experimental yield are equal. But in some cases, there were some negative interactions or even positive interaction. In the later case, the experimental yield is superior to the theoretical yield. So in the literature, we observe when we mix substrate, we have different nature and variable interactions, and their mechanism remain unclear. That's why we wanted to study the potential interaction between different categories of substrates, alone and in mixture, in dark fermentation. To do so, first, we studied a single category of substrate, which corresponds to 8 substrates studied individually. It was mainly reconstituted food waste and energy crops. Then, after this study, we analyzed another category, the mixture category, which was composed of 7 mixtures of the 8 individual substrates, with different composition in the mixture. For these 15 substrates, we analyze the composition, the sugar contents, the soluble extractable sugar contents, proteins, and lipids. Regarding fermentation, we measure the soluble metabolite production, the final concentration of these metabolites, and gas composition over time. The main objective of the study was to compare the yields of the different substrates studied. So we did BHP, it's the Biochemical Hydrogen Potential assays, to determine the hydrogen yield. So here you have the different conditions applied. We also made some modelization according to the Gompertz model to get some kinetics parameters, the maximal yield, the maximal production rate, and the lake phase. Regarding the results, here you have the yield for the hydrogen production for the single category of substrate, for the 8 individual substrates. We can classify these substrates according to their performances in hydrogen production. So you have the first family, which corresponds to a high production with a yield superior to 130 milliliters of H2 per gram of volatile solids. Then you have the intermediate family for an intermediate production of hydrogen. And then you have the low family, which corresponds to a low production of hydrogen. Based on this classification, we created different mixtures of substrates. So we had initially a mixture of reference where the composition of each family was well balanced. Then from this mixture of reference, we modify the composition by either doubling or halving the raw percentage of a given family. Here, as an example, you have the modification for the high production family. Regarding the results for the mixture category, we firstly compare the experimental and the theoretical yield for the 7 mixtures studied. Here you have the theoretical yield for the 7 mixture. And in blue, you have the experimental yield that we get during BHP assays. So as you can see here, we have an experimental yield that is superior to the theoretical one independently of the composition of our mixtures. And we get a mean gap of 40%. So we concluded that we observe positive interaction for our mixture substrates. But why do we have this interaction? First, we decided to take a look at the kinetics parameters, and more in particular, the hydrogen production rate. So we compare this production rate between the single category and the mixture category. And we observed that we had a faster hydrogen production for the mixture category compared to all the single substrates studied. But maybe we can also expect we have a faster hydrogen production, but maybe we can expect to have a more efficient hydrogen production in mixture conditions. So we also compare the hydrogen production efficiency ratio that I presented earlier. As a reminder, when the closer the ratio is to 1, the less hydrogen is consumed during homoacetogenesis. We use this ratio as an indicator. And we observe that it seems we have a trend that the mixture substrate has a higher hydrogen production efficiency than for most of the single substrates. So we concluded that we have a higher HP for mixed substrate that can show that we have less hydrogen consumed by homoacetogens. So we hypothesize that we have a faster hydrogen production in mixture condition that can prevent the consumption of H2 by homoacetogens. We also wondered if we can observe a correlation between the hydrogen yield and the sugar contents of our different substrates. In the literature, we have several examples of a linear correlation between the hydrogen yield and the hydrogen yield of single substrate and the soluble sugar contents. But in our case, we also have mixture of substrates. So we were wondering if it's possible to also get the same linear trends. So as you can see here, we have a linear correlation for all our substrates studied, including mixture substrates. To complete this data, we also add the results of Guo et al. And Molo et al. Study. And we can see that we obtain a correlation that is similar to the literature results. So it seems possible to predict the hydrogen yield based on the sugar contents of a given substrate or even a mixture of substrates. As a final figure, we also realized a principal component analysis to observe potential interaction for different variables for all 15 substrates. So as you can see here, there is no significant correlation between the content of proteins, lipids, and hydrogen yield. But we can see there is a strong positive correlation between the hydrogen yield and the HPE, as it was expected. We also observe positive correlation between the hydrogen production rate, the butyrate final concentration, and the sugar content, as I presented previously. Regarding butyrate concentration, we can conclude that this pathway is the most favorable for hydrogen production. As a conclusion, we observed a synergy, positive interactions when we are working in mixture conditions. We observed a faster hydrogen production, and we hypothesized that it can prevent the consumption of H2 by homoacetogen. However, we need microbial analysis to confirm this hypothesis. We also observe a positive linear correlation between the soluble extractable sugar contents and the hydrogen yield, and these results are in accordance with the literature. We would like also to get deeper in the understanding between the correlation between the composition of a given substrate and the hydrogen yield. That's why we would like to study the bioaccessibility and the complexity of the organic matter, maybe identify a new correlation with hydrogen yield. So this study can give a better understanding of mixing interaction, even if microbial analyses are still needed to confirm our hypothesis. And it seems possible to predict the hydrogen yield of a given substrate, even if it's in mixture conditions. Thanks for your attention.